I was muted. Oh, that means my last class was muted. That's okay, I'll just copy this class over. All right, okay, so plan is to finish up MO theory and start chapter 10. I got a lot of demos to get through today. So let's just review a little bit. All right, we built our MO diagrams last class. Today we're going to place the electrons. So let's just review how we made these MO diagrams. So MO stands for molecular orbital theory. We're combining atomic orbitals, treating electrons like waves to make resulting molecular orbitals. When we combine two atomic orbitals, how many molecular orbitals do we get out? Two, yes. One is bonding, it's lower in energy, and the other is anti-bonding, it's higher in energy. So we're including the idea that electrons are waves, they can combine in phase or out of phase. So we have to combine all those ideas together. Bonding orbitals, MOs, they have in phase atomic orbital overlap, they're in phase, and they have electron density between atoms. Anti-bonding molecular orbitals, they are out of phase atomic orbital combinations, and they lack electron density between our atoms. They weaken bonds when we put electrons in them. So what I like to do is, and I came up with this kind of analogy in office hours, two atomic orbitals combine to make two molecular orbitals. Molecular orbitals, they're like the children. All right, atomic orbitals, they're like the parents. All right, so you combine two atomic orbitals, those are the parents you're combining, and they produce some type of child. So we need to look at the column with the molecular orbitals and think to ourselves, who are your parents? And then we look at the atomic orbital column to figure that out. So take a minute and match the left side with the right side. Talk to someone around you. We'll go through this. Match those molecular orbitals on one side with the parents, the atomic orbitals on the other side, using the ideas, okay, is it in phase, out of phase, bonding, anti-bonding? Is it coming from an s orbital or a p atomic orbital? So take a minute and do that. So match the 1 through 5 with the A through F. Yes. There we go. All right, let's circle back now. All right, so let's match the children with the parents. So let me work through the molecular orbital side from the bottom to the top. So let's look at F real quick. This is the strategy I go through. I ask myself, is it bonding or anti-bonding? And then I ask myself, I squint my eyes and think, did you come from s orbitals or did you come from p orbitals? And then the last question I ask is it a sigma interaction, this head-on type of overlap between atomic orbitals, or is it a side-by-side interaction? And what do we call that kind of interaction? Pi. Yeah, so those are the three main questions you need to ask yourself. So this first one, are you bonding or anti-bonding? Anti. Yeah, so the giveaway that this is an anti-bond, a bond weakening molecular orbital, is that we have this dotted line between the atoms themselves. So those big black dots are representing, those are the atom centers. So see how we have this line essentially cutting that bond in half. So this is a bond weakening molecular orbital. If we put in electrons in there, we'll weaken the bond. So this is an anti-bond. All right? Another question we can ask ourselves is, who are your parents? Which atomic orbitals do you come from? S orbitals or P orbitals? What do we think? What do they look like? Yeah, they look like S orbitals. It's a child of S orbitals. So that's what we're going to look for. S orbitals combining in an to produce an anti-bond. So how do we get an anti-bonding orbital? What kind of phasing there? We want to look for in phase or out of phase? Out of phase. So what number goes with F? 5? Yeah, so 5, if you thought 5, yes, this is out of phase. Yes, it's sigma, but it's between what parents? P orbital. So this one's not correct. But you got 2 of the 3, but you missed the S part. So it's actually number 3. Out of phase combination of S orbitals give us this molecular orbital. Okay, let's move on to, so then let me ask you, since we, whoops, oh, sorry, my hand slipped. Where are we? Okay, so let's take a look at 5. These 2 parents, all right? So it's easy to mix up number 3 and number 5. 5 is what kind of interaction? This one or this one? It's a sigma interaction, yeah, so we need to look for a sigma bond, but is it going to produce a bonding or anti-bonding orbital? Anti, all right, and so we need to look for the molecular orbital, the child, that looks most like P2P orbitals, but is anti-bonding. So 5 goes with which letter? D, yes. So you see D has that dotted line between the 2 atom centers as well. So this is an anti-bond as well, but made between 2 P orbitals. Oh, I forgot to mention. So this is an anti-bond, specifically sigma anti-bond, and the other one was also a sigma anti-bond, but between S orbitals. So that's the big difference there. Let me do this better. So that one goes there, that one goes there. Okay, so let's do, I skipped over E. All right, E. So questions to ask. Is this bonding, anti-bonding? Who are your parents? S or P? And then finally, what kind of interaction is it? Is it sigma or is it pi? So what question can we answer first, do you think? If you squint your eyes, can you see who its parents are? These are your atom centers. Can we make this between 2 S orbitals like this, combining 2 S orbitals? No. So this MO's parents are actually 2 P orbitals combining this way. All right, and what kind of overlap do we call that? Pi, yes. All right, so where's our pi interaction? Is it 1 or is it 4? 1, yeah, so E is actually going to go with number 1. And we know this because we see, all right, so see how there's no dotted line between the atoms themselves? Yes, that there's not technically electron density between the 2 dots, but because they're above and below the atom themselves, we still have electron density between the atoms, just not necessarily where we would draw that imaginary line of where a chemical bond would reside. So here we have a bonding orbital, specifically a pi bonding orbital. And so that's produced from in-phase combinations of p orbitals. Okay. What about C? C. Do we have a sigma or pi interaction? Sigma, so sigma meaning that the 2 parents, they're combining in a head-on orientation. And who are its parents, S orbitals or P orbitals? P orbitals, yeah. And so we see, which one is it? What number? Number 2? 2, yes, number 2. And so you see that the overlap is happening between these 2 lobes that are in the same phase. They're both not colored there. All right, so that's C, okay. And then last one is B. Okay, who are its parents? S orbitals or P atomic orbitals? P. And so we see what kind of overlap's happening. Head on, side by side, side by side. So what do we call that type of molecular orbital? Pi star, yeah, the star, why do we put a star there? Why is this anti-bonding? It has the dotted line indicating that this is a bond weakening molecular orbital. We lack electron density between the two atoms themselves. See how they're kind of like pushing away? And so since this is pi star, we need to look for what kind of phasing between the two atomic orbitals. They need to be out of phase. So that's where the last one goes. This is number 4. Okay. All right. And so we have one left over that we didn't do. A is an orphan. All right, A is a lonely orphan, and we need to figure out who its parents are. So let's draw what we think the atomic orbital combination would make to get picture A. So what kind of bonding interaction is it? Sigma? Okay, yeah, sigma. So it's head on. And then who are the parents? S orbitals. And so then finally, is it bonding or anti-bonding? Bonding. It's bond strengthening because we see electron density between the atoms themselves. So this is sigma. You say it's bonding between s orbitals. So this person's parents look like this. How do I make a bonding orbital? A bonding orbital in terms of phasing. What should I do to the phasing? Match or mismatch? Match. So I'm just going to shade in both of them. So I make it deliberate that they both have the same phase. When they combine to get this stable bonding orbital there. All right. Okay, so those are all of those skills of thinking, combining atomic orbitals to make molecular orbitals. What we're essentially doing is combining wave functions of the atoms to make new wave functions of the molecule. What we're essentially doing is solving the Schrodinger equation, but just a little bit differently and a little bit more simplistic. I'll mention and remind you guys I have the midterm 3 review session this Sunday. It's in your Carmen calendar. There's a page, there's documents, there's a Zoom link. It's in this room. And then I'll go to Costco afterwards, hopefully, if I'm not too tired. All right. Before we go back to this question, let's now, because we stopped at this slide on the other day. So let's place these molecular orbitals energetically. We already determined who these molecular orbitals' parents are. So we can place these orbitals somewhere along the molecular orbitals in the middle of this diagram. All right? So we need to ask ourselves all the same questions. A is what kind of orbital? We said that it was sigma. It was a sigma bonding orbital, but between what type of atomic orbitals? Between s orbitals. So let me number these positions. I'll call it 1, 2, 3, 4, 5, 6. So where does molecular orbital A go in terms of these molecular orbitals numbered here? We already determined that it's a sigma bond made from s orbitals. So what position does it go in? 1, yes. Perfect. Okay. D, what did we say that was? Sigma or pi? Sigma, but it's sigma star, yes. But it's made between what kind of orbitals? P orbitals, yeah. So where does this molecular orbital go energetically? Does it go here in spot 2 because that's sigma star? No. What's the problem with this sigma star? It's made from s orbitals. Yeah, so number 2 actually goes with which one of these pictures? Goes with F, yeah, so sorry, I'm kind of skipping around. So that one's actually 2. D, which we just talked about, is number 6. All right, okay, B, what did we say this is? We said that's pi. Pi what? Star. Pi orbitals can only be made by p orbitals, so it has to go in spot what? 5. And then E, what kind of orbital MO is E? We said it's pi, and so that one has to be spot 3 because it's bonding. And so B and E, spots 3 and 5, they differ by is it bonding or anti-bonding. They're both pi, they're both made by p orbitals, but one strengthens the bond, one weakens the bond. And then finally C, where does C go? Spot which one? 4, yeah, because it's a sigma head-on interaction. Made between p orbitals. You can tell by the little lobes on the side. Isn't that fun? I like this. I like the pictures. I like the pictures. Okay, so let's talk about the strength of MO diagrams and how useful it can be. So let me just delete these real quick. Let's actually place the electrons for this nitrogen example, all right? And see and compare its Lewis structure to the MO diagram. So let's draw the Lewis structure of diatomic nitrogen. So that means doing the 6 steps. So what's the first step? What do? Count electrons. So we got 2 nitrogens. Each nitrogen has 5 valence electrons. So I need to place 10 electrons total. Right? There's no central atom, so I can just go ahead and write nitrogen, nitrogen. That's 2 electrons already, so now I just start completing octets. It doesn't matter where I start, so 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so maybe you're wincing because this looks really wrong, and that's okay because we're not done yet. All right, so we just placed the electrons. Now we check octets. So we see, does one of the nitrogens, does it not have a satisfied octet? Is there a problem? There is. This second nitrogen is lacking some electrons in its octet. How many more electrons does this nitrogen need to fulfill its octet? 2? No, it's 4. Yeah, it needs 4 more. There's 2 from the bond, 2 from the lone pair. So it needs 4 more electrons. So does that mean I can just draw more electrons? No, because then that's too many. I've drawn now, 14 electrons, and we can't do that. So what we're going to do is just move electrons over. So how many more multiple bonds should I make to that second nitrogen to fulfill its octet? 2 more. So what I'm just going to do, I'm going to go boop, boop, and then I'm going to redraw this molecule so it has a triple bond. And then we still have 2 lone pairs on nitrogen. Okay, there we go. You count up the electrons, you still see it's 10, but now you see nitrogen has a triple bond, right? So in last class, we talked about the 3rd way we calculate bond order. This, us just looking at diatomic nitrogen, and I see a triple bond. That's the first way we calculate bond order. That's just like, am I looking at a single line, 2 lines, that's a double bond, or 3 lines, that's a triple bond. But with molecular orbital theory, we have a very specific way we calculate bond order. We count the number of electrons in bonding orbitals, subtract electrons in anti-bonding orbitals, and divide by 2. So what we're lacking right now in our MO diagram is electrons. We didn't place the electrons yet. I have the diagram, there's just no electrons. So let's do that. So let's look at this MO diagram for nitrogen, and let's fill this out for nitrogen. Right? So note what we're looking at. These 2 interactions, these are between 2 s orbitals. And then I have another interaction happening between 2 p orbitals on 2 different nitrogen atoms. So this side is 1 nitrogen, there's another nitrogen. And so if we write the electron configuration, or at least understand how many valence electrons are on 1 nitrogen atom, tell me. On 1 nitrogen. 5. So, but there's 2 nitrogen atoms, so total, both nitrogen atoms are donating 10 electrons each, or sorry, total. So, you know, I can draw it this way. So there's 2 electrons here, 1, 2, 3. 2 electrons there, 1, 2, 3. So the job of the MOs, the molecular orbitals in the center, is I just want to rearrange these 1, 2, 3, 4, 10 electrons coming from atoms. I want to put them in the center within the molecular orbital picture, following all of our typical rules. Right? So all I'm doing is taking those 10 electrons, the same 10 electrons I used for Lewis structures, but I'm putting them in the molecular orbitals instead. So let's go ahead and do that. So the reason I'm doing 10 electrons is because each nitrogen is giving up 5 of its valence electrons. So let's go ahead and draw them in. 1, 2, 3, 4. And then what's special about this pi, these pi MOs, what do I have to do here? I got to spread them out. So 4, 5, 6, 7, 8, but in the end it doesn't matter because it fills. And then there. But sometimes it does matter. Okay, so those are all 10 of my electrons. So let's go ahead and calculate bond order. So we take bonding electrons, subtract anti-bonding, divide by 2. So how many total bonding electrons are there? 1, 2, 3, 4, 5, 6, 7, 8. And then how many anti-bonding? 2. So I can do 8 minus 2 over 2. And what does that equal? 3. Does that agree with our Lewis structure? What does our Lewis structure say? Triple bond. MO theory says it's a bond order of 3. Yep. Okay. Isn't that great? So let's do one more example. Let's do oxygen. All right. I'll just quickly draw the Lewis structure for you. Oxygen, there's 6 electrons for each oxygen times 2. That's 12 electrons I place. 2 oxygen atoms. So 1, 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Based upon the octet deficient oxygen right here, how many multiple bonds should I make? Just 1. So I'm just going to, I went up a slide because I want this MO diagram. And so I'm going to move one of the lone pairs right there. And so we see, what is the bond order in diatomic oxygen? 2. What do you think the MO diagram is going to say? It's going to have a bond order of, what do you think? 2. So let's check for ourselves. All right, so how many electrons do I need to put in my center molecular orbitals? How many electrons? It's the same number we did with our Lewis structure, because these atomic orbitals, these MOs, it's all the valence shell, all right? So there are a total of 2 oxygen atoms, right, 2 oxygens, times 6 valence electrons each, so we're going to put 12 electrons in the center there, right? I could go ahead and draw in the electrons in the atomic orbitals, but I don't want to. I'm just going to draw them in the MOs because that's what we care about right now. So I'm going to rearrange those 12 electrons into that center column. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the last 2 electrons go where? In pi star. But what do I have to be careful about here when I put the last 2 electrons? Spread them out, yes, so 11, 12, so in the same spin. Okay, so let's calculate bond order, but we kind of have an inkling of what it's going to be, but let's calculate it. How many total bonding electrons? 8, and then how many anti-bonding electrons? 4, so I can highlight those. So 1, 2, 3, 4, 5, 6, 7, 8, those are my bonding, and then these ones are anti-bonding. And so 8 minus 4 over 2, that's a bond order of 2. Does that agree with our Lewis structure? Yes. MO theory literally explains everything, but it's a lot more complex to do so. You know, it's fine enough to, you know, draw Lewis structures and all that, but it doesn't explain absolutely everything. You know, we use valence bond theory to just describe, you know, hybridization and multiple bonds, but we don't always need to apply valence bond theory, only in certain cases where other theories, more common simplistic theories, just don't suffice. Okay, so we're placing electrons now. So let's put all of the electrons together. So all of the second period diatomics. I have boron, carbon, nitrogen, oxygen, diatomic fluorine, and neon. So I place the electrons for you. And so what you're looking at are the 2s interactions and the 2p interactions. I place the electrons for you. We can go ahead and calculate bond orders here, all right? So if we look at diatomic boron, you can see there's a total of 1, 2, 3, 4, 5, 6 electrons placed. If you look at boron, it has how many? 1 boron has how many valence electrons? 3. So 3 valence electrons, but there's 2 borons, so that's why there's 6 electrons there. Right? So I want us to understand how many electrons to place for each of these. So let's go ahead and calculate bond order for boron. It's a lot easier when I just give you the structure. So we just need to do bonding electrons minus anti-bonding divided by 2. But let me show you a trick. In all of these molecules, we have a completely filled S interaction. See how the sigma and sigma star and the 2 S's, they're completely filled. So what we can do, these essentially cancel one another in this equation. If there's 2 bonding electrons minus 2 anti-bonding electrons, we can just ignore any electrons coming from this inner core because they end up canceling each other out. It's 2 minus 2. So we can just ignore those. So if we ignore the S interactions and just look at the P interactions, I see that there are 2 bonding electrons in boron minus how many anti-bonding in just the p interactions? 0. And so what is the bond order in diatomic boron? 1. Bond order of 1. Okay. So let's move on to diatomic carbon. Do you want to ignore these s electrons? Yeah, let's just ignore them because it's bonding, anti-bonding, they cancel. So now, how many bonding electrons are there in diatomic carbon? 4. How many anti? 0. Divide by 2. So we see a bond order of 2. Cool. All right, so let's think ahead to nitrogen. So as we go across the periodic table, boron, carbon, nitrogen, each atom is gaining 1 electron. So if you look left to right and see the difference of these diagrams, aren't we just adding 2 electrons for each element, each molecule of this series? We're just adding 2 electrons. So let's think if there's another way we can predict going from diatomic carbon to nitrogen, if we could predict the bond order. So to get to nitrogen, don't we just have to add 2 electrons to this diagram? And if we add 2 electrons, where are they going? What kind of orbital is it going to go into? This sigma bonding orbital. So doesn't that strengthen the bond? And that's what we see here when we calculate the bond order of nitrogen. We already did, but we can do it again. There are 6, we're adding electrons to a bonding orbital, so what we see is bond order actually goes up, all right? And it changes once, so we could calculate a bond order of nitrogen to be 3, just like we did before. When we go to oxygen, we add 2 more electrons, but where are those electrons going now? Are they going into a bonding orbital? No, they're going into a anti-bonding. So will the bond order go up to 4 at this point? No, it's actually going to go back down because the 2 electrons we add are going to anti-bonding orbitals. So instead of increasing this bonding number, we're actually increasing the anti-bonding number. So that's why bond order starts to go down. But let's calculate it. How many bonding electrons in oxygen? 1, 2, 3, 4, 5, 6. And then how many anti? 2. So it's 6 minus 2 over 2. So the bond order in oxygen is 2. But we already calculated that. And do note that, see the ordering switched appropriately, all right? It switched a little bit, but we still calculate it the same. Okay, what do you think diatomic fluorine is without even doing the bond order calculation? It's probably going to be 1, and then neon is probably going to be 1? It's going to be 0, yeah. But let's calculate it, prove it for ourselves. So fluorine, 6 bonding electrons minus how many anti-bonding electrons? There are 4 electrons in pi star divided by 2, that is 1. And then finally neon, there are 6 bonding electrons, 6 anti-bonding electrons. So 6 minus 6 over 2 is 0. So that's how we see diatomic fluorine has a bond order of 1. Neon, diatomic neon has a bond order of 0. So does diatomic neon exist? No, it doesn't. It does not exist. That it is not stable to put electrons, or energetically favorable to put electrons between 2 neon atoms. So we have a bond order of 0 to indicate that. Okay, so other information we can draw from these MO diagrams, because they're all in front of us and easy to read here, is predicting their magnetism, all right? So magnetism, we can have substances that respond to a magnetic field or they don't respond to a magnetic field. So when there's unpaired electrons in the MO diagram, so in the center column, we get paramagnetic materials. When everything is spin paired, we see diamagnetic materials. So what we're looking at is the electrons in the boxes. So based upon that definition I just said, boron, diatomic boron is what? Dia or para? Para, yeah, because there's unpaired electrons. Simple as that, right? What about diatomic carbon? Dia. Nitrogen? Diamagnetic, everything's paired. What about oxygen? This one is going to be paramagnetic, which is interesting. I'm actually collecting some liquid oxygen right now as we speak, and I will show you it responding to a magnetic field. And then diatomic fluorine, diamagnetic, right? Everything's paired. We're not going to do neon because it doesn't exist, right? So that's it. Magnetism just means, are there unpaired electrons or not? Right, all of these examples are neutral, charge neutral. So let's look at some other examples. So I'm going to keep this diagram up because it's nice to just reference it. Let's look at these examples. So for which of these compounds, which ones are paramagnetic? So what we're doing is looking for unpaired electrons, right? If we have unpaired electrons in their diagrams, then they're paramagnetic. So we see of two of the options, we have nitrogen and oxygen. We already said nitrogen, it's diamagnetic, so there are no unpaired electrons there, so we can eliminate that one. But oxygen, is it paramagnetic? Yes, it says so right there. See, two unpaired. So this one is paramagnetic. All right, but now we have an issue. Now we're working with anions. We have nitrogen 2 minus, and we have oxygen 2 minus. But I didn't give you diagrams for that, so are we screwed? No, we're not screwed. What are we going to do? What are we going to do? Just add 2 electrons to both of them. So let's do that. So for nitrogen, where are we adding those 2 electrons? In the pi star. Perfect. Like that. And again, remember to follow Hund's rule. But then when we add 2 electrons to oxygen, what happens? It becomes diamagnetic. So we see the 2 answers are the anion of nitrogen, but oxygen's neutral one. And so you just got to draw it. Add and remove electrons as necessary, whether you're working with a cation or an anion. All right, so that's magnetism. So let's still talk about anions and stuff because it's useful. All right, so here I'm asking which molecule of the pairs, so nitrogen and the anion, oxygen and the anion, has the larger bond enthalpy. So essentially, I'm asking you, which bond is stronger of the pairs? All right, so really, since we did this in like chapter 8, right, I asked you this question all the time, which bond is stronger, which one is longer, which one is shorter? In the end, it all comes back to bond order trends. And that's the one, learning objective with molecular orbital theory is calculating bond order. So this entire question is just calculate the bond order of these things and compare. So since we're looking for the stronger bond, what kind of bond order are we looking for? A high one or a low one? A high bond order. Strong bonds have high bond orders. Strong bonds are also short. All right, so if the question said which bond is shorter, we would also just look for the higher bond order. All right, so everything just comes back to bond order. But let me show you a trick. We don't actually really need to calculate bond order here. We can just think about the bond order calculation, right? Bond order is equal to bonding electrons minus anti-bonding electrons over 2. So we can strengthen a bond by increasing this number, the number of bonding electrons. But if we remove bonding electrons, do we strengthen or weaken the bond if we remove bonding electrons? We weaken it, yeah, just based upon the number mathematically. What if we add electrons to an anti-bonding orbital? Do we strengthen or weaken the bond? Weaken it. Bond order goes down because you're making the minus anti-bonding number bigger. But what if we remove anti-bonding electrons? We strengthen the bond because you're removing a bond-destroying electron, right? Like a parasite on the atom. So we can do this without actually calculating anything because we can look at nitrogen, all right? And then we're comparing it to nitrogen anion. So if we look at nitrogen and ask ourselves, okay, to make an anion, we add 2 electrons, but where are those electrons going? In what kind of orbital? Into a anti-bonding. So adding electrons will do what to the bond? Weaken it or strengthen it? Weaken it. So which one is stronger? And to the neutral one, yeah. So we didn't actually have to calculate it. We could just kind of think our way through it. Or you can calculate it. You'll get that nitrogen has a bond order of 3 and the anion has a bond order of 2 or something. Yeah, okay. All right, we can do the same thing for oxygen. Oxygen right here, anion, we're adding 2 electrons. What kind of orbital are we adding those electrons? Anti, So adding electrons will do what to that bond? Weaken it. So which bond is stronger, neutral or anion? Neutral. Okay, now let's do carbon. So look at carbon, it's right here. Add 2 electrons, where are we adding them? Into what kind of orbital? Bonding, so what are we doing to the bond? Strengthening it. So which one's stronger? The neutral or the anion? The anion, that's it. So we didn't even have to calculate anything. Just us understanding, oh, adding electrons to bonding orbitals strengthen them. Adding them to anti-bonding orbitals weakens the bond. And again, it's because of the bond order question, or the equation. All right. Or, and I mentioned, so in the end, everything comes back to bond order. So I'm asking here, which one has the longer bond? So what am I really asking? Bigger bond order? Smaller bond order, yes. Weak bonds, small bond orders have long bonds. Small numbers. So we're looking for the lowest bond order here. So it's just a bond order question again. But this time, I have some cations here. So, except this one. So boron, right here. We add 2 electrons, so what do? Strengthen or weaken the bond? Strengthen. So which one has the longer bond, neutral or anion? Neutral. Okay. Fluorine. Oh, this time we are making a cation. So what do we do to make a cation? Remove electrons, but which ones? Which electrons do I remove? Yes, anti-bonding, but you remove the topmost. And so in this case, it happens to be anti-bonds. All right, so if we remove these anti-bonding electrons, what do we do to the cation? Are we strengthening or weakening that bond? Strengthening it, because since we remove anti-bonding electrons, we are making the minus anti-bonding electron a smaller value, so the number's overall bigger. So which one has the longer bond, neutral or cation? Neutral. Okay, and then carbon, cation. So carbon's right here. We're removing 2 electrons. We're removing what electrons? Bonding. So we do what to the bond? We weaken it. So which one has the longer bond, neutral or cation? Cation, perfect. And we didn't have to calculate a dang thing. You used all concepts. All right. Okay, how do we feel about that? Good? All right, so let's finish off this chapter, talk about oxygen again. So I hinted at that oxygen is a paramagnetic molecule. So let's bring back its Lewis structure. Paramagnetic, what does that mean? What do we look for? Unpaired electrons. Look at the Lewis structure of oxygen. Is there any indication that there are unpaired electrons in there? No. So does the Lewis structure explain oxygen's paramagnetism? No. But what does explain oxygen's paramagnetism? MO theory. Yeah, we got to actually do the MO theory here. And so we already did oxygen. Oxygen has how many electrons? 12. And so if we fill up this table, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you see that these 2 electrons right there are paramagnetic and can respond to a magnetic field. And so I have that demonstration here. All right. Let me go back to this table right here. So we said oxygen is paramagnetic. What about nitrogen? Is nitrogen paramagnetic? Will it respond to a magnetic field? No, because everything's paired. So let me show you this. I have to do my camera thing. Okay, so I have a magnet right there. You see the magnet? All right, can you see it? Okay, so I have some liquid nitrogen. What did we say about liquid nitrogen? Will it respond to this big old magnet? Do you see anything sticking to that magnet? No? Me pouring this actually has a purpose. I need to make the magnet cold. All right, so we don't see any nitrogen sticking to that magnet. So let me I've been collecting liquid oxygen all day. Let me put this down. There it is. It's very cold. So let's see what liquid oxygen does. Do you see that? That is liquid oxygen. 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 Is that responding to that magnetic field? Yes, it is, yes. See it? Yes, and so why is it sticking to the magnet? Using MO theory terms, there's unpaired electrons, yes. And so in nitrogen, are there any unpaired electrons? No, so let's just, I'll prove it to you. I'll do nitrogen again. I'll do nitrogen again to show you that it does not look like that. Is there any sticking with nitrogen? No, there's not. Because there are no unpaired electrons. Very good. Okay, I've never done that demo before, and I think it's pretty cool. Okay, and so can valence bond theory just explain why oxygen is paramagnetic? Valence bond theory. Can it? No. Can a Lewis structure explain why oxygen is paramagnetic? No, but what can? MO theory, yes. All right, so let's look at another example of MO theory here. And that's for a more complex diatomic molecule like carbon monoxide, right? Carbon monoxide. So in this example, if you look at the supplemental information, we don't give you carbon monoxide, its MO diagram. So if this were to come up on the exam, we would give you the MO ordering for any complex molecule like this. But what you can do is place the electrons, all right? So if we're working with carbon monoxide, we're combining a carbon atom and an oxygen atom. I give you the MOs right here. So we got sigma, sigma star, et cetera. How many electrons am I going to put into this molecule? 10. How do we get 10? 4 from carbon, 6 from oxygen. So hopefully you know what carbon monoxide looks like. I'm just going to do it for you. So carbon monoxide is a triple bond. Looks like that. So what do you think the MO diagram is going to say the bond order is after we fill it in? It's probably going to say 3. So let's see if that happens. So how many electrons do I put in the MO again? 10, because 4 from carbon, 6 from oxygen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so let's zoom in here and let's calculate bond order. Do you want to ignore the S interactions? Yeah, okay. So just looking at the P interactions, how many total bonding electrons are there? 6 minus 0 over 2 equals 3. Isn't that great? Yes. MO theory, it explains everything, though it is the most complex. All right, so I just wanted to show you one more complex one for fun. So everything we've looked at are just diatomic atoms, or molecules. 2 atoms always make a line. And so when we have this linear, like geometrically linear combination of atomic orbitals, the MO diagrams are a little bit simpler. Here's water. Water is bent. So its molecular orbitals, one, it's working with hybrids. And so it gets a lot more complex. We'll never test you on this. I just wanted to show you how complex it can be, even for a molecule as simple as water. And so you see different phasing here. And what I wanted to draw your attention to were how they labeled the molecular orbitals. If we look at these symbols, psi, they say psi 3, psi 4. If we remember back in chapter 6 what psi stood for, it stands for wave function. Because what are electrons? Waves, yeah, and so that's the significance here. We're essentially solving the Schrodinger equation when we look at MO theory. All right, and just to show you how smart you are, because chapter 9's done now, so that means homework is due on Monday. Monday! Who said Tuesday? Okay, just to show you all how smart you are, I just wanted to show you my PhD dissertation. You actually have all the tools to read it and understand it. So here's the title. It's called Investigation of Molecular Crystalline Systems Using Ultrafast Time-Resolved Infrared Spectroscopy. It's a fancy way of saying stuff you already know. Investigation, fancy way of saying this is what I studied. Molecular and crystalline. Those are molecules and ionic compounds. We talked about those in chapter 2. Ultra fast means really fast. Infrared is part of the electromagnetic spectrum, a little bit lower energy than visible light. That's it. Those are all words you know. And so what I wanted to show you is the MO diagram for those quadruply bonded compounds that we talked about earlier, right? A quadruple bond has a bond order of 4. And so the components of a quadruple bond are a sigma, 2 pi's, just like our triple bond, but the 4th component is not another pi, but a delta bond. And so I wanted to show you these interactions. Here are the parents. Tell me, what kind of interaction is between these two d orbitals? Sigma, and is that what this is? Heck yeah, and the phasing, look at the phasing. They're in phase, aren't they? And then, so these are interactions between d orbitals. Okay, d orbitals look like butterflies. So it's kind of similar to the side-by-side overlap of p orbitals, but what you see are 2 different pi interactions between d orbitals. So that's what those 2 lines are there. And then ask yourselves, is this phasing in phase or out of phase? That's in phase, and so that's why this is pi bonding. And then the last one is a delta bond, and so we see that these are in phase. The butterflies are kissing one another like this, all right? And so imagine what the antibonds look like. They're going to be the same, but what's going to be different? The phasing, that's it. So look at the sigma star. Is the phasing out of phase? Yes, it is. And if we look at here, we look at the pi star interactions, we also see out of phase delta interactions. So you can understand this. I hope you feel very, very smart. Okay. And then I guess the last thing, there are 2 molybdenum centers here. And just believe me when I say that there are 8 valence electrons to place. So if we place 8 electrons on this diagram, 1, 2, 3, 4, 5, 6, 7, 8. Calculate the bond order. What is it? All of those 8 electrons are in bonding, so the bond order is 4. And this is what kind of bond? Quadruple, yes. So you know everything to answer that. All right. So that concludes midterm 3 material. All right. Very little calculations, very little calculations. I'll point out that midterm 3 is usually very high performing, just because there's a lack of calculations, right? Okay, so remember I do have that review session on Sunday. All right, we have to move ahead with chapter 10. The plan is to, do as much as we can today, and then on Tuesday, we have to do a little bit more chapter 10, but then the second half of the class we'll do a midterm review. All right, so we're gonna get through. I still have more demos to do. All right, I got 30 minutes to do these demos. So let's talk about gases. We have to bring our calculators back out, so we'll celebrate bringing our calculators back out by blowing something up. Okay. I also have a guest here, and I want to impress them. So, all right, let's think about gases. I know we went from, a lot of theories, things we can't really see, to now we're talking about gases. So there's definitely a big shift in how we are thinking about chemistry. We're kind of going back to the land of things that we can touch and feel. So let's gauge ourselves with, let's think about the characteristics of a gas. I have hydrogen gas right here, our favorite. Yes, our favorite, our hydrogen balloon. So imagine, what does this hydrogen balloon, think about the particles inside there. So the H2 particles, let's think about its characteristics. Common gases we interact with are like the air that we breathe. So thinking about that, are gases usually homogeneous or heterogeneous, we think? Is the air I'm breathing the same as the air you're breathing? Yes, so that would mean that gases are typically homogeneous. Yes, yes. Okay. All right, think about our hydrogen balloon and the particles inside it. Is that sample mostly empty space, or all those particles packed in together? Empty space, great. All right, is our gas sample up here, is it rigid, or can we easily compress it? Rigid? It's rigid? I can just deform the balloon, right? It's easily compressed. I can compress it. I can change it. Yeah. Like a balloon animal. Why can you make balloon animals? Because the gases are you can easily move them around and stuff. Yeah. No, it's cool. That's why we're doing this. All right, think of the particles inside the sample. Is there limited motion, or are the particles free to move however they want? Unrestricted motion, great. And then finally, based upon I guess there's two more, the particles inside the gas sample, are they strongly attracted to one another, or are they weakly attracted to one another? Think about how far away they are from one another. If they're really attracted to one another, shouldn't the particles be close together? So is that what we see in gas samples? No, so they are weak, okay. And then finally, based upon those ideas, unrestricted motion, easily compressed, what do we think reactions with gases do? Do you think they happen really fast or slow? Fast, okay, so let's check. Let's check for ourselves and celebrate that we have to bring math back. Okay, so got my hydrogen balloon here. I asked them to put coloring in it. So we'll see what happens. All right, so remember the ears thing? This is very loud. Everyone, do Dumbo ears. Okay? Yes, everybody. Oh, hold on. They gave me the bad lighter. Okay. Hooray, calculators. Oof. That wasn't that loud. Was it green? No. It wasn't. Okay, perfect. It was supposed to be green, but it wasn't. All right, so yes, calculators are back. They ran out of oxygen, so it was just hydrogen, so it wasn't as loud. It wasn't as loud because there was no oxygen in there. Okay. Maybe one of these days I'll let one of you blow up the balloon. I don't know, maybe. Okay, so let's also think about more conceptually about gases, because we are making a big change from earlier. So like water. We understand water usually as liquid water, but sometimes you'll encounter solid water, which we call ice. But then we can also encounter water as a gas, too, and we call that what? Water vapor, yep, or steam, yes. So let's think about what that means on a particle level, all right? Turning a liquid into a gas, oftentimes, normal people, we call that boiling. Right, so I have a particle representation of what liquid water looks like, the H2O particles inside there, H2O liquid. All right, and the particle level diagram where those water molecules, they're all packed in together because this is a condensed liquid sample. So think about, we take that liquid water, we heat it up, we boil it. What does that steam look like? What is the particle representation of what H2O gas or steam look like? Is it A, B, C, D? What do we think? It is C, yes, where really all we're changing, it's still H2O gas, and this is a misconception that I want to just address and make sure that we're not falling for. When we boil something, when we change something from a liquid to a gas, that's a physical change. So are we changing the identity of water? No. So are any chemical bonds broken or made? No. All we're changing is the distance between the particles themselves. That's it. So you can see both pictures have the same exact water molecules, just copy and pasted in two different places. A, B, and D, in order to get these pictures, you actually have to break chemical bonds. And that's what kind of change? Is that physical? No, that's a chemical change. But that's not what's happening here in a phase change. This is a physical change. So all we're doing is changing the distance between particles. Okay, let me do, okay, no, not this one. So common gases we've interacted with on our periodic table. We've talked about elements in their most standard state or most stable state in chapter 5. We said most metals were solids, and then a lot of the nonmetals were gases. And so kind of just putting all of that together, all of our noble gases are gases at ambient conditions. So what I mean is at earthly conditions. So like at 1 atmosphere of pressure, at room temperature, you will find these elements as gases. And you'll hear me constantly refer to conditions as on Earth, because I want you to think, okay, on Earth, you will find water typically as a liquid. But if you were on Mars, do you think water would be H2O would be in a liquid state? I don't know. Yeah, it might be in a solid. I don't know. Is it cold on Mars? Yes. Okay, then it's probably going to be a solid on Mars. So I always have to be careful with the conditions I'm talking about. So in this slide, these substances are typically gases on Earth, because that's like our typical temperatures. Noble gases, diatomic hydrogen, nitrogen, oxygen, fluorine, and chlorine. Right? And the reason these are gases is that they're relatively light particles, and they have very weak attractions to one another, so they're more likely to adopt gaseous states. Right? Those are our elements. There are also compounds that are gases as well. We'll talk about those. Okay. Gas misconceptions. Okay. Let's go to Party City and get some helium balloons. So we go to Party City, we ask the person, fill up this balloon with helium. So when they fill up that balloon with helium, how does the volume change of the balloon? Yeah, it goes up. Just like if we blew up the balloon with our lung air, the volume increases. Very good. Increase. Yes, they fill it up with air, or helium. Okay, so the helium particles, they go inside the balloon, increase the volume, but how does the mass change? Don't overthink it. It does what? It increases, yes, but helium balloons float. I would think that the mass would decrease. Some of you might be sitting there thinking that, oh, I thought helium balloons float, so I thought that the mass would have to decrease. But here's the thing. If the volume's increasing because we're adding particles of helium, helium has mass, right? So for every helium particle we put in, we are adding 4 AMU of mass. To a certain point, we are, in fact, increasing the mass. So do not think, just because helium balloons float, that when you add helium to a balloon that the mass goes down. No, you're still adding particles into it. The reason helium balloons float is because they are less dense than air. All right, so kind of like a boat, the water it displaces creates buoyancy. Same thing with helium. Helium is, in fact, lighter, on average, lighter than air, so its density is less dense than air. So the air that it displaces causes that buoyancy and why it floats. So it's the difference in density that makes helium float, not that, oh, you're removing mass when you add helium particles. That's not the case. And that's a common misconception. Okay. All right, properties of a gas. So how we can measure them. So we've already talked about temperature and volume and stuff. So a new one is pressure. All right, so pressure is defined as a force per unit area. And so a common pressure unit we use here on Earth is ATM, or atmosphere, where 1 atmosphere is referenced to the pressure at sea level. And it's because humans are kind of selfish and we want earthly conditions to be 1, right? And then we reference everything to Earth conditions, right? So 1 atmosphere, that's like earthly conditions. So what pressure is, because I don't like the unit of atmosphere. 1 atmosphere really means nothing to me other than, oh, that's Earth. We can also use the relationship 1 atmosphere is also equal to 14.7 pounds per square inch. Those pressure units are the same. So where atmospheric pressure comes from is the air around us. Most of us, we think of air as being very light. We walk through, it's not something we really notice. But if you take a column of air above your head and go all the way to the stratosphere, and you collect all of the gas in that column of air, all the gas particles, all of the the nitrogen, the oxygen, the CO2, all of it, and you put it all in a bowl, and you weighed it. If you weighed all of those particles in that column of air, it would be about 15 pounds. It would be 14.7 pounds per square inch of column above your head. So that's where atmospheric pressure is coming from. It's literally coming from the particles that are above our head out into space. That's where pressure comes from. So here are some conversions between pressure units. I don't think you have to memorize these. I believe we give these to you on the exam. I'm not sure. I will look into that. All right. But again, calculators back out. We can use dimensional analysis to convert between these. All right. So let's see if we remember how to do this. All right. So we are given a value, a pressure value of torr. And we want to get to atmospheres. So I have all of these pressure conversions. So I see, 760 torr is equal to 1 atmosphere. So using dimensional analysis and canceling out units, 760 is going to go where in my fraction? On the bottom. And then 1 ATM goes up top, and then your answer is right there. Okay? So 760 torr is a little bit more than 1 atmosphere. Okay, let's go from atmospheres to kilopascals. So I'm going to start with 1.2 atmospheres. I'm going to use the conversion that brings me to pascals. So 1 atmosphere is 101.325 pascals. Pascal is named after a scientist. Pascal is the SI unit for pressure. It's 1 Newton meter squared. So when we do this conversion, that big 101.325 number, is it going to go on the top or the bottom? On the top, very good. Okay, we do remember dimensional analysis, very good. It's been a while. It's been a good while. Pascals, whoops, Pascal, 1 ATM on the bottom. And so are we done? No, the question asks for what? Kilopascal. Ooh, is that something we need to memorize? No, that's just a metric prefix, right? So how many pascals in a kilopascal? 1,000. 1,000 pascals is a 1 kilopascal. All right, and so then we get a better number because a pascal, there's a lot of pascals in an atmosphere, and so changing it to kilopascal puts it into a nicer number to look at, 122. That's like a nice round number. All right, instead of like something with scientific notation. I think if you frequent boats use kilopascals as their pressure gauges. Okay. All right. You want to hear a really bad joke? Yes? Okay. Okay, so remember, Pascal's the SI unit for pressure. So Einstein, Newton, and Pascal, they're in heaven because they're dead, and they're playing hide and seek. So Einstein, he closes his eyes and turns around and he starts counting down from 100. And so Pascal goes running off to go hide, but Newton stays where he is and he draws a 1 meter square around where he's standing. And so when Einstein's done counting and he opens his eyes, he goes, "Newton, I found you. Why didn't you go hide?" And then Newton goes, "No, you didn't find me, you found a Pascal." Because he's a Newton standing over a meter squared. I told you it was a bad joke. Okay, all right, so how we measure atmospheric pressure is through a barometer. All right, so before they did the lab renovations, there used to be a barometer on the wall that you could read, but you all did the gas lab, right? And now it's just this digital thing that the TA just wrote on the board for you, right? So it used to be an instrument you would read like this, where it had graduations. So before, how they would measure atmospheric pressure and where the term millimeter of mercury came from, because that's a weird pressure unit you saw, right? This is where it came from. We have this pool of mercury. We have this inverted tube in it where there's a vacuum inside of the tube. And so if we think about it, do vacuums exert any pressure? Are there any particles inside that vacuum? No, there's not. So when atmospheric pressure comes down and pushes on this vat of mercury, it pushes back up on the inside of this tube. So when we read a barometer, the weight of the mercury inside this tube is equal to the pressure on the outside. All right, and that's when we read our barometer or our atmospheric pressure reading. And so the weight inside here is equal to the external pressure on the outside. So we're always trying to equalize this pressure, what's on the inside and what's on the outside. And so the reason we use mercury is it's so much more dense than water. If we replaced this barometer with water, the height of that column that has to equal the weight of the pressure outside would have to be 34 feet high. So in order to read a barometer made of water, you'd have to go up like 4 flights of stairs to read the meniscus. So that's why they use mercury. And so that's where the term millimeter of mercury came from. You set this experiment up, and at earthly, 1 atmosphere pressure, that column of mercury is how tall? 760 millimeters tall, so 3/4 of a meter. So it's about this tall, right? And that's something like, that's a benchtop, apparatus you could have. So that's where millimeter of mercury comes from. It comes from this experiment, the height of that mercury to equal the weight of the atmosphere on the outside. Okay, so what you see here is that the force inside this tube is equal to the force outside the tube coming from the atmosphere. So constantly, we need to think about gases equalizing themselves with the pressure, the external pressure around it. Gas samples can do a lot to change its environment. We can change the volume, we can change the temperature or the pressure of that gas sample to equalize the forces and the collisions that are coming from the surroundings from the inside. And so those adjustments to volume, temperature, pressure, those are things we're going to track with some of the named gas laws. I have 14 minutes left. Yeah, I think I can do the demos. Yes, so we're always trying to equalize those forces, right? So with that in mind, let's look at a manometer, which measures the pressure of a gas sample in reference to external, like 1 atmosphere of pressure. So let's look at this gas sample. Here's a gas. It exerts a pressure, but it's also in contact with external pressure where there's a column of mercury separating these two systems. We have the gas sample, and then we have 1 atmosphere of pressure coming from the outside. So I want you to tell me, based upon this picture, does the gas sample have more or less pressure than the external pressure, 1 atmosphere on the outside? That might be hard to answer, so let me phrase it differently. Who's winning, the gas or the outside? The outside is winning. Yes, the outside is winning. By how much? By 10 centimeters, yes. With 10 centimeters also equal to how many millimeters? 100. Yes, 100 millimeters. So yes, just from this picture, we say, oh yeah, the external gas, or the external pressure, the world is winning versus the gas sample. So that means the gas sample has less pressure than the outside world. So can you tell me, what is the pressure based upon the numbers we have here? What is the pressure of that gas? What is it? 660, yeah, 660 millimeters of mercury. Okay, all right. See, I told you, isn't it easier? So who's winning in part B? Gas. Gas is winning. By how much? 5 centimeters, so 50 millimeters. All right, so that means the pressure of this gas is equal to what? 810 millimeters of mercury. Yeah, so basically what we're saying is that this gas is exerting enough force, all right, pressure, to overcome external pressure plus all the weight that comes from 5 centimeters of mercury, or 55 millimeters of mercury. So that's why the pressure of the gas sample is plus 50 millimeters of mercury, or torr, whatever, because it's winning here. So here, if I draw the thing, the gas has greater pressure. All right? Okay, good. Yeah, when I phrase it the way the book phrases it, no one gets it. But when I ask you who's winning, then everyone gets it. Okay, so then which of these samples exerts a pressure greater than 1 atmosphere? A or B? B, yes. But if we just started with that question and I didn't give you the hint of who's winning, then it might have been a little bit more difficult. All right, so we have to factor in that differences in height of the manometer to the correct side based upon who's winning. So we see in set B, the gas is exerting more pressure than the external surroundings. So we see the gas pressure is higher than the atmosphere. Okay, so we talked about pressure. All right, so in that example, we used millimeters of mercury, but there's also torr. Torr and millimeters of mercury are the same thing. So 1 torr is equal to 1 millimeter of mercury. Oftentimes I like to say torr because there's less syllables, just so you know. I like to say torr rather than millimeters of mercury because that's a lot of syllables to say, right? But we oftentimes are using pressures in atmospheres because what we're going to learn about is the ideal gas law equation, which we've all used already in the gas laws lab. And in order to use this equation, we just need to be careful with our units inside this equation. So for using the ideal gas law, our R constant has a specific unit. So usually we want to be working with pressures in atmospheres. So it's useful for us to know the conversions, how to get to atmospheres if we're in some other unit. We'll talk about, so pressure is new. We've already talked about volume. Typically, we're working in liters, but sometimes milliliters, so do know the conversion between those common volumes. Number of moles of gas, we know about that, how to calculate number of moles of gas from like a gram amount using the periodic table. And then finally, temperature. With temperature, typically our thermometers in lab are in Celsius, but again, with the ideal gas law, we want to be in Kelvin. So I believe we do give you the Kelvin conversion, but do make sure when you put in temperatures into our equations, you don't put whatever temperature you want. You put the temperature required for that calculation, and it's typically in Kelvin. All right, side note. So we are talking about temperatures and pressures a lot. So a common shortcut that we use is talk about standard temperature and pressure. So this is kind of close to like ambient conditions, but STP, or standard temperature and pressure, means the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. It's easier for me to say STP conditions than to say 1 atmosphere and 0 degrees Celsius. So that's why we have this reference point that scientists oftentimes use, and it's called STP. So just know if I say STP, it means 0 Celsius, 1 atmosphere. But with the Celsius, remember, typically we want that in Kelvin. So 273 Kelvin is the way to go if you're using the ideal gas law. All right. So all of these measurements, they're related to one another in the named gas laws. And I have 7 minutes to do these demonstrations. So we'll look at some of these named gas laws and how temperature, pressure, and volume are related to one another when we change the condition that a sample is in. All right, so like for example, I have this balloon, it's a set amount of sample. I can change where this balloon is. I can put it in this environment or this environment. We have the same amount of gas, it's just in different environments, so sometimes we see changes in temperature or volume based upon the environment it's in. So these named gas laws are talking about samples just changing their environment. All right? Yeah, okay, so let's do this. So the first named gas law. So these are very, very old and ancient observations and laws that scientists with very limited tools could do. They just, measured the temperature, volume, and pressure of gases. They could do that. So this is actually how they figured out what a mole is. Someone in one of our classes asked me, how do they figure out like the Avogadro's number, how they figure it out? This is how they did it. It's via gas laws, that they were able to kind of play around with gases to see what happened. So Boyle, he noted that at a constant temperature, all right, volume of a gas varies inversely with the pressure exerted on it. So what we see is when we increase the pressure of a gas, or you squeeze it, the volume goes down. But the thing is, temperature has to remain constant. Or if we decrease the pressure of a system, we see volume increase. And so they're inversely proportional to one another. So we can write this equation to talk about pressure and volume relationships between two states. So N is constant, and I should add that T, temperature, is constant here too. So I have my demo here. I don't think I need goggles. Okay, I got a snowman made of marshmallows. Does anyone know how to make a marshmallow? No? No one watches the Food Network or like whatever? Okay, so what a marshmallow is you take molten sugar, you add gelatin, and then you beat the crap out of it with a mixer. The point of the mixer is to do what? Make air bubbles, make it chewy, make it, soft, right? We're putting little air bubbles inside the marshmallow. So there's tiny little gas bubbles in here, all right, filled with gas. So I have a little vacuum pump here that can reduce the pressure just inside this bell jar. So right now the marshmallow is experiencing just 1 atmosphere of pressure. But when I turn this vacuum pump on, I'll reduce the pressure in here. So based upon Boyle's law, because all of this is happening at room temperature, what should happen to our marshmallow man? Will he get bigger or smaller? Think about it, and then I'm going to do it, and we'll see. Turn you on. Okay. Do we see it? What's he doing? Come on. These are really old marshmallows, I've been told. Okay, so hopefully someone in the front can see. Marshmallow Man is growing. He's growing. He's definitely growing. Look how puffy he is. All right? Yeah, so he's puffy. There you go. So we do see, we reduce the pressure inside there. So if you heard it, you heard a big whooshing. What is that whooshing? All the gas going back into the bell jar, because now it's back to ambient conditions again. So he got bigger because pressure, when I turned on the vacuum pump, reduced inside the bell jar. Pressure went down, so volume went up. All right, so let me do the second demo. It's here. I like this one. At a fixed pressure, so meaning on Earth. Because does the pressure really change day to day? It's 1 atmosphere right now. It's going to still be 1 atmosphere tomorrow, all right, for the most part. We see temperature and volume are proportional to one another. So temperature goes down, volume goes down. So I have a fixed sample, this balloon sample, and I have liquid nitrogen. Liquid nitrogen is really cold. So what do you think will happen when I dunk this balloon into cold liquid nitrogen? It's going to shrink, yes. So I love this demo. Because we get caught up in misconceptions. The volume decreases, but is there still gas in there? Yeah, there is. So when we do this demo in front of kids, and they're funny because they're not very bright, or no, they think chemistry's magic. So they think, oh yeah, see, the volume goes down, so there's no more gas, right? They think that, but that's not true. Because when I bring this balloon back to room temperature, what's going to happen? What's going to happen? It'll get big again, because did the gas go anywhere? No, it's still in there, but kids, they think it's magic, right? They're like, oh, the gas like disappeared and came back, but no, all we're doing is changing the temperature of it and the kinetic energy of the particles inside, all right? So you could do this forever. All right, so we'll stop right there. So remember chapter 4 homework due. We're going to continue on chapter 10 on Tuesday, but the second half of class we'll do midterm review.